Good afternoon. As Hero pointed out, I'm going to be talking about cutting and turning, which supplements the shock absorption issue. I'd just like to point out my co-author there, Tobias Underdown, whose work I'm going to present is partly his doctoral thesis work. Why study turning? Well, as someone has just alluded to, it can be dangerous in terms of giving high loading about the knee and ankle, and quite often there's knee ligament problems, almost an epidemic of knee ligament problems. So it's a very serious challenge to a lot of team sports to be able to cope with that continuous turning maneuver. But not only that, we've heard in some of the previous sessions a lot about loading, the loading that's accumulated through a training session, through a match. And part of that loading, a big part of the loading in my opinion, is cutting and turning. So to learn more about it, to understand negative and positive aspects of it is a good thing. We're looking at it from the perspective of both initially footwear and then more recently surfaces. And it's the latter research I'm going to share with you. If you look at what tests are out there at the moment, mechanical tests to try to predict linear friction, that's an example which is used by FIFA as part of their battery of tests to give a star rating to a surface, a matched surface. But the loads that are administered are not realistic to a player in a real game-like situation. And also, they do not reflect typically how a player perceives the grip and traction. So there's quite a lot of documented evidence now that these are not the best in terms of giving you meaningful results. So FIFA are looking towards perhaps supplementing these types of measurements with player data. Not easy because there's an inherent variability in what we do. So it's very difficult to try to have a controlled assessment using players, but it's worth a go to see if it can be achieved. The aims of this research then were to develop a standardized test protocol of a surface performance during a rapid game-like cutting maneuver. And we used a test procedure that we had previously developed from testing soccer boots. I'll share that with you in a second. The idea was to collect detailed high-speed motion from the boot surface interaction. If you look in the literature, there's not a lot of three-dimensional high-speed data on how the boot interacts with a natural turf or artificial turf surface. So this was, if you like, a first attempt to try and do that. The idea was to identify key assessment criteria that could possibly be used to characterize a surface, and then use that data as a comparative database to assess performance characteristics of different varieties of football turf. By football turf here, I mean artificial turf. So I'll use that term. Many years ago, we did quite a bit of work with different soccer boot manufacturers to try and look at outsole performance on natural turf, both outdoors and also indoors. That's a lot of effort. Imagine a wheelbarrow, lots of heavy soil being carted in and out of the lab. So it's much preferable to do it outdoors, even though there's some lack of control inherent in that. We developed a procedure which is based on one single maximal turn, rather than a series of turns. We found that the maximal turn was much better at differentiating between soccer boots with different outsole stud characteristics. So we adopted that same philosophy for the surface testing. The philosophy then was to look at game-like maneuvers. From match analysis, we knew that these types of maneuvers, a complete change in direction and a V-cut, were the most common. If we had to choose just one, we would go with the V-cut because it includes some rotational aspects. For the boot analysis, we made sure that the boot's conditions were unknown to the player. Obviously, it's not so critical for the surface appraisal. Just have to make sure that the boot is constant. With the preferred turning direction and maximal effort to place greatest demand upon that boot surface interaction. This was the study that we did. We used 19 semi-professional players, approaching at about 80% speed, doing a V-cut maneuver, and exiting at maximal speed. That's what we found was most reproducible. We looked at 9 pitches in total, 3 artificial, 6 natural, in 3 different countries. Why did we do that? That's a lot of effort, I know. It's because of the different types of grass in different parts of Europe, different pile densities, including different types of football turf designs. So we wanted to get a wide spectrum, but a manageable spectrum. All were assessed beforehand in terms of being satisfactory, having passed all the battery of tests that FIFA have got as part of their FIFA quality concept. So they were regarded as 2-star, top-level surfaces. We measured the foot and lower leg movements at high speed. There's a reason for that. I'll get back to that. So with outdoor testing, a little bit of a challenge. So we had to have an array of cameras around the turning area. This is a large calibrated area, so we could modify the turn location so that when turf was disrupted, we could move to a fresh area. So every 2 or 3 players, we would move the location completely. We had 6 high-speed cameras synchronized with a high-speed video camera, and timing gates on the approach and exit. So we could get turn time, an accurate ground contact time, approach speed, exit speeds. Here's an example of a player doing the maneuver, and you can see here the turn, the calibrated area, and we would ask the player to gradually move in that calibrated zone and adjust the timing gates accordingly. Different conditions, because you had changing light conditions from bright sunlight in Spain to darkness. The cameras had to be continually adjusted for the optoelectronic tracking. That's a lot easier now, but when we did this experiment, it was quite a challenge, but we got there in the end. We also had to cope with rain. You see the cameras are covered there with plastic bags, and excessive sunlight. We used a fairly straightforward lower limb 3D model, which was a shank segment, and then 3 segments on the foot, rear foot segment, midfoot, forefoot. The reason we did that, because it was easier when looking at the breaking the skill down into the ground contact phase. Typically, you landed with heel first contact, then in mid support, the foot was flat, and then push off phase, forefoot contact only. So we could actually look in detail at what was happening with respect to certain parts of the foot which were in contact with the soil. And also 3D data, you could quite easily go to an anatomical perspective to look at supination, eversion, inversion angles, plantar flexion angles, and so on. But a detailed appraisal of the foot movements relative to the soil. Here's just an example of the video frame. The video was synced, so if it was necessary, we could digitize the video and feed it back into the 3D analysis. But the primary role was to act as a first rough guide where heel strike and toe off were. And then we would use the kinematic data to make a more precise judgment. So you've got heel strike and toe off, and also flat foot being identified. To check our heel strike and toe off, we used force platform data back in the lab with one of the subjects and recreated the conditions outdoors. So there's a typical force trace where you'd have heel strike and toe off, and we would verify our kinematic parameters to get those events correct. So we've got various algorithms here that we used to do that. So 3 simple phases then. Phase 1, initial landing phase. This varied between individuals. For some individuals, it was extremely short. There was barely a heel-first contact, but there was always a heel-first contact in the group that we had. Mid-support phase, when the foot was flat, and then a last phase, heel rise to toe off. In those phases, we concentrated on the rear foot segment for phase 1, mid-foot segment for phase 2, forefoot for phase 3. We need to be careful with the data processing, because if I take you back, to the ground reaction force curve, you can see there's a high frequency aspect of the curve here. So there's a good clue that you've got rapid segmental motions as well in that phase. And that was indeed the case. So this was the rapid accelerations of the rear foot segment. And this is for a given subject between the green is the artificial surface, the blue is the natural turf surface for the same player. So this is just that phase. There is a steeper slope, so a greater rate of deceleration. So in that case, jerk for the football turf for this particular player. But you only see those differences if you've maintained high frequency components of the signal. If you went with just filtering the data with 15 hertz, so you've got the data up to about 15 hertz, virtually no difference between the two surface conditions. So you need that high frequency data, and that's facilitated by sampling at a high rate. We normalized foot position to the center, so it was nicely zeroed, so we could calculate from heel strike, zero displacement.